Okay, let's run through another example. This is a slightly different way of doing things. Oops, what happened there? I don't know. Okay, that's okay. Da-da-da. I don't know what's happening. Okay, so this is an article that talks about neural general circulation models for weather and climate. This is also AI, but slightly different approach on weather and climate. General circulation models, or GCMs, what the are the foundation of weather and climate prediction. GCMs are physics-based simulators that combine a numerical solver for large-scale dynamics with tuned representations for small-scale processes such as cloud formation. Basically, we call these parameterizations, where the processes that are not explicitly resolved are parameterized based on data, various other approaches. Recently, machine learning models trained on reanalysis data have achieved comparable or better skill than GCMs for deterministic weather forecasting. However, these models have not demonstrated improved ensemble forecasts, so one integration is fine, but they don't yet do the ensemble, so multiple realizations to cover the potential evolution of the real world, or they haven't shown sufficient stability for long-term weather and climate simulations. Here, we present a GCM that combines a differentiable solver for atmospheric dynamics with machine learning components and show that it can generate forecasts of deterministic weather, ensemble weather, and climate on par with the best machine learning and physics-based methods. Neural GCM is competitive with machine learning models for the 1 to 10 day forecasts and with the European Center for Medium Range Weather Forecasts ensemble prediction for 1 to 15 day forecasts. With the prescribed sea surface temperature, Neural GCM can accurately track climate metrics for multiple decades, and climate forecasts with 140 kilometer resolution show emergent phenomena such as realistic frequency and trajectories of tropical cyclones. For both weather and climate, our approach offers orders of magnitude computational savings over conventional GCMs, although our model does not extrapolate to substantially different future climates. So you can see this is very different than the previous two podcasts. Our results show that end-to-end deep learning is compatible with tasks performed by conventional GCMs and can enhance the large-scale physical simulations that are essential for understanding and predicting the Earth system. So this is a schematic of how that works: forcing, noise, inputs, and the outputs. So there is learned encoder. I mean, obviously I'm just being superficial here. So this is the structure of the neural GCM model. There's the overall model structure showing how the forcing, noise, and forcing, noise, and inputs are encoded into the model state xt. That's the beginning of the integration. So here is the numerical model with its dynamical core, and you have data-based learned physics, and you insert physics tendencies from learned physics and combine with dynamic tendencies from the model to into a ODE solver, which is a implicit explicit ordinary differential equation. These are all nonlinear numerical representations of the nonlinear Navier-Stokes equations. So you get learned decoder directly here, and you get the ODE solver to give you the solution at xt plus 1. So you went from xt integrated to xt plus 1. 1 is a time step which could be whatever, 6 hours, 1 hour, depending on the stability and other things. Then you combine them and produce outputs at yt plus 1, which is just a way of saying that you have translated from x to y. Okay, so here's the learned physics xt going into neural networks and then producing physics tendencies, which is repeated n times here to iterate to get the learned decoder. So basically ensures iterative convergence, but you still have emergent solutions. I'm saying it in a very loose way. Okay, so the new model state xt plus 1 can then be fed back into another time step or decoded into model predictions. So here you're looking at learned physics module, which feeds data for individual columns of the atmosphere. So the atmosphere is, you can see the sphere is split into grids and vertical columns. So that's the vertical column there of the atmosphere. So that basically tells you how the physics tendencies are created by learning from the encoder here. Very brief, sorry, you can go back and follow up on the paper. Neural GCM is a differentiable hybrid atmospheric model that combines the strengths of the traditional GCMs with machine learning for weather forecasting and climate simulation. To our knowledge, Neural GCM is the first machine learning based model to make accurate ensemble weather forecasts with better CRPS than state-of-the-art physics-based models. It's also, to our best knowledge, the first hybrid model that achieves comparable spatial bias to global cloud resolving models, can simulate realistic tropical cyclone tracks, and can run AMIP-like simulations with realistic historical temperature trends. AMIP is where it's not coupled to the ocean. The temperatures at the bottom are ocean temperatures are prescribed. There is a land that interacts with the atmosphere, so it's a standard process. So you can see that running multiple ensembles of the dynamic model is very expensive, whereas this Neural GCM can save you on that by producing ensemble forecasts without running the dynamical model so many times. Overall, Neural GCM demonstrates that incorporating machine learning is a viable alternative to building increasingly detailed physical models for improving GCMs. Compared with traditional GCMs with similar skills, Neural GCM is computationally efficient and low complexity. Neural GCM runs at 8 to 40 times coarser horizontal resolution than ECMWF's integrated forecasting system IFS and global cloud resolving models, which enables 3 to 5 orders of magnitude savings in computational resources. For example, Neural GCM 1.4 degree simulates 70,000 simulation days in 24 hours using a single tensor processing unit versus 19 simulated days on 13,824 central processing unit course with an X shield. Extended data is given in table 1. You can follow up. So massive savings, not only in computational time but obviously energy, and the faster you can do it, the quicker is your forecast, right? You want to forecast for the next 6 hours with multiple ensembles, then you want to be very quick. You cannot take longer than 6 hours to make a 6-hour forecast, right? This can be leveraged for previously impractical tasks such as large ensemble forecasting. Neural GCM's dynamical core uses global spectral methods, and learned physics is parameterized with fully connected neural networks acting on single vertical columns. Substantial headroom exists to pursue higher accuracy using advanced numerical methods and machine learning architectures. Our results provide strong evidence for the disputed hypothesis that learning to predict short-term weather is an effective way to tune parameterizations for climate. So how do you go from weather to climate? So short-term weather predictions can be an effective way to tune parameterizations to climate, so that NWP and climate predictions are not two different systems, which is what happens now. Neural GCM models trained on 72-hour forecasts are capable of realistic multi-year simulation. When provided with historical SSCs, they can capture essential atmospheric dynamics such as seasonal circulation, monsoons, tropical cyclones, and so on. However, we will probably need alternative training strategies to learn important processes for climate with subtle impacts on weather timescales, such as a cloud feedback. So there are fast timescales with impacts on lower frequencies, weather to climate, low frequency rectifications, and so on, that still have to be dealt with. Models based on physical laws and empirical relationships are ubiquitous in science. We believe the differentiable hybrid modeling differentiable hybrid modeling approach of neural GCM has the potential to transform simulation for a wide range of applications such as materials discovery, protein folding, and multi-physics engineering design. Exciting news. I wanted to have these 3 podcasts just to say AI for weather and climate is a real thing, and they are moving fast. Even though they may not replace dynamical weather forecasts, they will complement them in very beneficial ways. So overall forecasting, especially for each sector, will be advanced very quickly based on these combinations. Let me leave that there and come back to the next topic, which I don't know what it is. Okay.